Now let's talk about dimensional analysis. Any physical situation can be described by a certain familiar properties, for example, length, velocity, area, volume, acceleration. These are known as dimensions. Of course, dimensions are no use without magnitude being attached. We must know more than something has a length. It also must have a standardized unit such as a meter, a foot, a yard, etc. attached with it. Dimensions are properties which can be measured. Units are the standard elements we use to quantify these dimensions. So what exactly is the difference between dimensions and units? Dimensions are basic type of quantities that can be measured or computed. For example, length, time, mass, temperature, electric current. Unit is a standard amount of the dimensional quantity. There is always a need of a system of units. For our class, we will always use the SI system of units as discussed in the last lecture. Now, how are dimensions important? Dimensional analysis is a useful technique in all experimentally based areas of engineering and physics. If it is possible to identify the factors that are involved in any physical situation, dimensional analysis can form a relationship between them. The resulting expression may not at first sight appear rigorous, but these qualitative results converted into quantitative forms can be used to obtain any known factors from experimental analysis. So in dimensional analysis, we are not only concerned with the nature of the dimension, for example, it is its quality and it's not its quantity is what we are concerned about. Dimensions are basic types of quantities such as length, time, or mass, represented by, instead of using units, we're just going to call it L for length and T for time and mass for M. So whenever you see square brackets attached with numbers, that means it is not the actual unit, it is actually its dimension. We really don't know what unit it is attached to. So for example, volume, the SI unit is meter cubed, whereas the dimension is L cubed. For force, the SI unit is Newton, which is kilograms meters per second squared, but in terms of dimensions, we are going to call it meters, MLT minus 2. Similarly, energy or work is represented in joules, which is Newton meters, and its dimensions are ML squared T squared. Understanding that we don't know the units that are always know the units that are associated with the dimensions, but it helps us come up with fewer errors in our problems. Dimensionally consistent. Any equation describing a physical situation will only be true if both sides have the same dimension. That is, they must be dimensionally homogeneous or dimensionally consistent. Here's a word of warning. Pay attention to dimensions. Fewer errors in equations. Whenever you see an equation that's written out, please make sure that it is dimensionally consistent. It will avoid lots of headaches towards the end. Now let's look at an example of dimensional analysis. Analyze the dimensions of the following equation. 1, d equals vt, and d equals 1/2 at, where d is the distance traveled, v is the speed, t is the elapsed time, and a is the acceleration. Now, knowing nothing about these expressions, can you figure out whether these equations are possible or not? Let's try to figure this out. So, question number 1. D equals vt. D is the distance traveled. The SI system for distance traveled is always meter. So dimensionally, the right-hand side will be length, because length is a dimension of meters. V is the speed. Given that V is equals to distance over time, we can write the dimensions of V as distance over time, which can also be rewritten as L T minus 1. On the units for T are seconds, which mean dimensionally they will be time. Okay, when I plug this into my right-hand side of this expression, what do I get? I get L over T, and for T I get T. T cancels away, and I get length on the right-hand side and length on the left-hand side. So this means that this equation is dimensionally correct, and so this is a good equation. Okay, so we put a check mark there, and that equation is allowed. Now, let's look at the second expression. That is d equals 1/2 at squared. Again, the dimensions of d, which is distance, is length. Okay, now a is acceleration. A is acceleration, right? So the dimensions of A should be length per t squared. Okay? Once I plug that back into here, what should I get? Equals 1/2 length times t squared. And from the last expression, I know t is this. This cancels out, and I get 1/2 L over T on the right-hand side. On the left-hand side, I have only L. Okay? What does that mean? Is this dimensionally correct? No. So this is not possible. This expression is not possible.